In the previous lecture, we introduced the important notions of the range and null space of a linear transformation. Let us recollect and let us now focus on a finite dimensional space. So, we have a finite dimensional space V and another finite dimensional space W, and we have a linear transformation T from V to W. And then a part of this was what is known as NT, and a part of this was what was known as the range of T. Now, let us recollect the definitions. N of T is all those vectors in V which get mapped to the 0 vector, and let us recollect R T on this side is the collection of all those vectors in y in W such that there exists an x in V with T x equal to y. The NT is a subspace of V and the RT is a subspace of W. So, we have this situation where we have a linear transformation from a finite dimensional vector space to a finite dimensional vector space. On the domain side, we have the null space of T, and the codomain space we had the range of T, and the dimension of NT is what we called as nu T, and it was the nullity. It is called the nullity of T, and the dimension of range of T is what we called as rho T, denoted by rho T, and this is called the rank of T. And clearly, NT being a subspace of V, dimension of NT which is nu T is less than or equal to dimension of V, and dimension of range of T which we call as rho sub T must be less than or equal to dimension of W. Now, let us take dimension of W to be dimension of V to be n and dimension of W to be m. So, we have nu of T is less than or equal to n and rho of T is less than or equal to m. Now, let us look again this space V. In this space V is what we marked off a portion called the null space of T, and its dimension was nu T. So, this space in V we have a portion of V, a subspace of V which is called the null space of T, and it has dimension nu T. If it has dimension nu T, any basis for NT must have exactly nu T vectors. So, any basis for NT must have nu sub T vectors. So, let us take one such basis, call this as Bn, the basis for the null space, to be phi 1, phi 2, and there should be phi nu T be a basis for the null space of T. So, we have phi 1, phi 2 and so on, and phi nu T. These are vectors in the null space of T. These are linearly independent. These span NT, that means they form a basis for Bn. Now, if you look at the space V, it is an n dimensional space, and we have these vectors which are linearly independent in that space. There are nu T of them. In an n dimensional space, any linearly independent set of vectors can be extended to be a basis by appending suitable number of vectors. In this case, the dimension of V is n, we already have nu T vectors. So, we need n minus nu T vectors from outside NT, and they should be linearly independent, and together they will form a basis for. So, say we can extend Bn to a basis BV which consists of all these vectors, and we append exactly n minus nu t vectors in order that we get totally n vectors to form a basis for V. So, we can extend Bn to a basis BV for V by appending n minus nu t vectors, and these should come from outside n of t. So, from, and these should be linearly independent. So, n minus nu t linearly independence coming from V, but outside n of t. So, what happens is, now we are going to choose u1, u2 and so on u n minus nu t. So, n minus nu t vectors outside of n t, but in V, which are linearly independent. Then this set and this set of vectors and this set of vectors together will form a linearly independent set, and since there are n of them, they will form a basis for V. So, what we have done is, we have started from a basis for the null space of T and extended it to a basis for the whole space V. Now, let us look at on the image side. T is going from V to W, and on this side we have the range of T, and we know theta W is a part of the range of T. We have already seen that range of T is a subspace of W, and any subspace must contain the 0 vector, that we know, and therefore, theta W belongs to the range of T. Now, what happens to this vector phi 1 under the mapping T? Since phi 1 is in the null space of T, it will get mapped to theta W. Phi 2 will get mapped to theta W. Phi nu t will get mapped to theta W. In fact, everything in n t will get mapped to theta W. So, in particular this and all these fellows are going to focus on theta W. All the phi's are going to get mapped to theta W. So, we have first observe that T phi 1, T phi 2, T phi nu t are all going to be the 0 vectors. So, that is the first observation, because all these vectors are in the null space of T. Now, let us look at u1. T of u1 will be the value of T at the point u1, therefore, it will be in the range, but it will not be 0. It will be in the range, T of u1 will be in the range, but it will not go to theta, because if it had to go to theta, u1 must be inside this n t, but u1 is outside n t. So, u1 is going to r t all right, but it is going to in r t a vector different from the 0 vector. Similarly, u2 is going to go to a non-zero vector, un minus nu t is going to go to a non-zero vector. So, u1 will go somewhere there, u2 will go somewhere there, and so on, they will avoid theta w. So, we have T phi 1, T phi 2, T phi nu t is theta w, T u1, T u2 and T of u n minus nu t are all different from theta w. Now, consider any vector x in V. If you take x in V, any vector in V can be written in terms of the basis vectors as a linear combination. Now, we have basis consisting of these phi's and u's, and therefore, we must be able to write x as a linear combination of the basis vectors, namely therefore, we can write it as alpha 1 phi 1, alpha 2 phi 2 plus alpha nu t phi nu t plus those combinations which will involve the u 1 vectors also, b 2 u 2 plus etcetera b n minus nu t u n minus nu t. So, any vector x in V can be written as a linear combination of the vectors in the basis. We have now chosen the specific basis B V, and this B V consists of the 5 vectors and the u vectors, and therefore, we are able to write x as a linear combination of these 5 vectors and the u vectors. That says T x must be the t of the right hand side. Now, the right hand side is a sum, and linear transformations preserve addition and scalar multiplication. In particular, they preserve addition. Therefore, t of x plus y is t of x plus t of y. Therefore, t of a sum is the sum of the t's. So, we can take t individual terms. So, this will be t of alpha 1 phi 1 plus t of alpha 2 phi 2 plus t of alpha nu t phi nu t plus t of beta 1 u 1 plus t of beta n minus nu t u n minus nu t. This is because t preserves addition, t is a linear transformation, and therefore, t of a sum is the sum of a t, that is equal. Now, t also preserves scalar multiplication. So, t of alpha 1 phi 1 will be alpha 1 t phi 1, t of alpha 2 phi 2 will be alpha 2 phi 2 t phi 2. So, pulling out all the scalars, we get finally this is equal to t alpha 1 t phi 1 and then alpha 2 t phi 2 and finally alpha we should write it as nu t, alpha nu t phi t phi nu t plus beta 1 t u 1 plus beta 2 t u 2 beta n minus nu t t u n minus nu t. So, T x for any vector x, T x will have to have this form, which means the following. Remember, phi 1 is in the null space of T. If you recall that picture, we had phi 1, phi 2, phi nu t were all in the null space of T. So, they were all going to the 0 vector under T. Therefore, we had observed that T phi 1, T phi 2, T phi nu are all 0 vectors. So, using that fact, we get this alpha 1 t phi 1 must be 0, alpha 2 t phi 2 must be 0, alpha n nu t t phi nu t must be 0. So, all these are 0 vectors, they are not going to contribute anything. So, what we have is just p 1 beta 1 t u 1 plus etcetera beta n minus nu t t u n minus nu t. We will write it as beta 1 v 1 plus beta 2 v 2 beta n minus nu t b n minus nu t, where v 1 is t u 1, v 2 equal to t u 2 and so on, v n minus nu t is t n t of u n minus nu t. So, what have we achieved? What we have shown now is, if you take any vector in V, t of that will have to be of this form. So, any vector in x, x in V, t of x must be of this form. But all the vectors in the range of T are of the form T of something, T of some vector in V. So, therefore, all the vectors in the range of T must be of this form, but every vector in range of T is of the form T of x for some x in V. Hence, every vector in range of T, since it is of the form T of x and T of x must be of this form. So, every vector in the range of T is of the form beta 1 V 1 plus beta 2 B 2 plus beta n minus nu t B of n minus nu t. And these vectors V 1, V 2 are all T of something, and the V 1, V 2 therefore belong to the range of T. So, and V 1, V 2 etcetera V n minus nu t belong to range of T. So, we have here, let us get back to that picture. We have in the picture now u 1 went to V 1, that is T u 1, T u 2 is V 2 and so on and so forth, and we get V n minus nu t. So, in the range of T we have gotten hold of n minus nu t vectors, and every vector in the range of T is a linear combination of these V 1, V 2, V n minus 2. So, we get, if we call this set S as V 1, V 2, V n minus nu t, since every vector in the range of T is a linear combination of this is a spanning set for range of T. So, once we have a with starting from a basis for null space of T, which are the 5 vectors, we extended it to a basis for the whole space V, and looking at the image of these basis vectors, we got hold of a spanning set for the range of T. So, what we have therefore is, if phi 1, phi 2, phi nu t is a basis for the null space of T, and phi 1, phi nu t u 1 u n minus nu t is an extension to a basis for V, then T of the extending vectors. What are the extending vectors? U 1, U 2, U n minus t. These are the extending vectors. If you take T of them, you get U 1, V 1, V 2, V n minus 2. They form a spanning set for range of T. This is what we have. So, now this V 1, V 2, V n minus t is a spanning set for the range of T. Now, once we have a spanning set, we wonder whether this is going to be a basis. When will it be a basis? A spanning set will be a basis if it is also linearly independent, because a linearly independent spanning set is called a basis. It is already a spanning set, and we would like to ask, so natural to ask if this set S is a basis for range of T. Already we know it is a spanning set, we want to know whether it is a basis. Now, S will be a basis, the answer will be S. So, therefore, S will be a basis for range of T if it is linearly independent. So, we have to check whether it is linearly independent. When will it be linearly independent? A set will be linearly independent if the only linear combination that produces the 0 vector is the linear combination in which all the coefficients are 0. So, S will be linearly independent if we look at any linear combination of these vectors in S, and if it produces the 0 vector, 0 of what? These are all vectors in W, and therefore, if it produces the 0 vector in W, then this must imply all the coefficients must be 0. That is the only linear combination which can produce the. If this is true, then S will be linearly independent. So, let us check whether this is true. So, let us start with A1, B1 plus etcetera A n minus nu t V n minus nu t equal to theta w. To save our writing, we will use summation notation. This is summation j equal to 1 to n minus nu t A j V j equal to theta w. Now, what does that mean? We know that the V vectors are the images of the U vectors under T. So, remember V j was T of U j. This must be equal to the 0 vector. That says j equal to n minus nu t. Now, scalars can be put in and out of the linear transformation, because linear transformation preserves scalar multiplication. So, we can write it as T A j U j equal to theta w. Again, since T is a linear transformation, T of a sum is the sum of the T's. So, we can pull the T out of the summation notation and we get A j U j equal to theta w. Now, u1, u2 all these vectors are in V, and therefore, any combination of them will also be in V. So, let us call that whole thing inside as some x equal to theta w, where x is equal to summation j equal to 1 to n minus nu t A j U j is a vector in V. So, x is a vector in V and it gets mapped to the 0 vector. So, what we have got is, if A1 V1 A2 V2 A n minus t V n minus nu t is 0 vector, then this gives rise to a vector x which gets mapped to the 0 vector. If that is getting mapped to the 0 vector, x must be in the null space of T. If x is in the null space of T, why is x is the null space of T? Because T x is equal to theta w. Now, the phi 1, phi 2, phi nu were all basis for a null space of T, and x is a vector in the null space of T, and any vector in the null space of T can be expressed as a linear combination of the null space T basis vectors. So, x can be written as a linear combination I equal to 1 to nu t b I phi I. This is because the phi 1, phi 2, phi nu t form a basis for the null space of T. On the one hand, we have x equal to this, on the other hand we have x equal to this, and therefore, these two must be equal. Hence, we have on the one hand we had x is equal to j equal to 1 to n minus nu t A j U j. On the other hand, we have x is equal to b I phi I. So, these two must be equal to each other. Now, this can be written as j equal to 1 to n minus nu t a j u j plus summation I equal to 1 to nu t minus b I phi I equal to all these are in V, therefore, it is 0 vector. Now, we have a linear combination of the u vectors and the phi vectors, which gives the 0 vector. Recall that the u vectors and the v vectors together formed a basis for the V space. If you look at the way we constructed it, we had this picture in which we had the u vectors and the b vectors together forming a basis for V. So, since the u vectors and b vectors together form a basis, they must be linearly independent vectors, and therefore, any linear combination of them vanishes only if all the coefficients are 0. We have here a linear combination of the u vectors and the v vectors and the phi vectors to be 0, and since these are linearly independent, we get the a j is to be equal to 0 in particular, and we also have the b i's to be equal to 0 for 1 less than or equal to I less than 2. Thus, what is the conclusion? We started with a linear combination of the v's to be 0 and concluded that all the coefficients must be 0. So, hence summation j equal to 1 to n minus nu t a j v j equal to theta w implies a j's are all 0, and hence the v 1, v 2 etcetera be n minus nu t or linear length. We have already seen that they form a spanning set for the range of t, and now we have seen that they are also linearly independent. Therefore, S is equal to V 1, V 2, V n minus nu t is a linearly independent spanning set. So, hence the linearly independent spanning set for R t, and hence S is a basis for range of t. So, conclusion is you start with V and the space W, this is n, this is m say, and T is a linear transformation. Then you pick a part of it which is called the null space of T. You start with a basis phi nu t, extend it to a basis u 1 u 2 u n minus nu t. From there together we get a basis for V. Then look at only the images of this u 1 u 2 u n minus t, they give you V 1 V 2 V n minus nu t, they are all in the range of t and they form a basis for the range of t. Now, what do we get from this? The V 1 V 2 V n minus nu t is a basis for the range of t. Therefore, the number of vectors in the basis must be the dimension. There are exactly n minus nu t vectors in the basis. Therefore, dimension of range of t must be n minus nu t. Since V 1 V 2 V n minus nu t is a basis for range of t, and this has n minus nu t vectors, we get dimension of range of t is equal to n minus nu t. But dimension of range of t is what we call the rank of t. So, the rank of t is n minus nu t, or bringing the nu t to this side, rho t is the rank of t, nu sub t is the nullity of t, and n is the dimension of V. So, this simply says rank T plus nullity T equal to dimension of V. This is called the rank nullity theorem. So, let us summarize. We have the rank nullity theorem. The rank nullity theorem is the following: V W finite dimensional vector spaces over a field F, T mapping V to W linear transformation, then rank T plus nullity T is equal to n, is equal to dimension V. This is known as the rank nullity theorem. This is a very important connection between the dimension of the range of T, which is a subspace of W, and the dimension of nullity of T, which is a subset of V, subspace of V. So, let us again look at the picture. We have V, we have W, and then the null space of T is a linear transformation, and the null space of T is carved out of the space V, and the range of T is carved out of the space vector space W, and what it says is we already had, because n t is a part of V, we had dimension of n t which is nu t, and since it is a part of V, it must be less than or equal to dimension of V. And the rho t, which is the dimension of range of T, must be less than or equal to dimension of W, because it is a part of W. Now, what we have shown is that this nu t plus n t or nu t plus rho t is equal to n. We also had the rank nullity theorem, which says that the rank plus nullity is equal to the dimension of V. So, this is rho t, this is nu t is equal to dimension of V. Nu t is a non-negative, it is a dimension, it is a number. So, it is a non-negative quantity, and therefore, when you add a non-negative quantity to rank of T, you get the dimension of V. So, the rank of T must be smaller than or equal to dimension of V. So, we also get rank of T must be less than or equal to dimension of T B by rank nullity theorem. So, we have the rank cannot exceed the dimension of the space W, it cannot exceed the dimension of the space V, and hence the rank of T is less than or equal to both dimension of V as well as dimension of W. So, it cannot exceed the dimension of V, it cannot exceed the dimension of W. So, the rank of T is something which is controlled both the sides, the dimension of V as well as the dimension of W. Let us look at some examples of this rank nullity theorem. If you recall, we had the example V equal to F 3, W equal to F 2, and the linear transformation from F 3 to F 2 defined as T A of x equal to A x, where A was the matrix 1 0 minus 1 0 1 minus 1. We had seen this example in the last lecture, and we had found the null space of T to be the set of all vectors in V such that X is of the form alpha 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 belongs to F. And we found that nu T which is the dimension of n T is 1, because this dimension is 1 because the space is spanned by one single vector, namely 1 1 1. We had also found the range of T was all of F 2, and hence rank of T, the dimension of range of T, which is the dimension of F 2, was 2. Now, if you add the rank and the nullity, the rank is 2, nullity is 1, which is equal to 3, which is precisely the dimension of V, because V is F 3. And thus, we see that rank T plus nullity T is equal to dimension V, thus verifying the rank nullity theorem for us. Let us look at another example. Recall we had the other example V as F 4 x, and then we looked at the linear operator from V to V defined as the differentiation operator dp equal to dp by dx. And we had found the null space of T to consist of all constant polynomials, so that P x equal to a naught belongs to F, and the dimension of n T is 1 again, because it is spanned by the constant polynomial 1, and therefore, nu T is 1. And we also had the range of T to be the set of all polynomials which are in F 3 x, because when you differentiate you lose 1 degree, and therefore, the dimension of R T is exactly dimension of F 3, which is 4, and this is what we call as rho sub T, the rank of T. So, we have rho sub T plus the nu sub T is 4 plus 1, which is 5, which is the dimension of F 4, and which is what the dimension of V in this case was, because V was F 4. Again we see that rank T plus nullity of T is the dimension of V. Let us look at the last example we had previous time. We took V equal to F 4, and we took W to be equal to F 3 x. Polynomials of degree less than or equal to 4 is the vector space V, polynomials of degree less than or equal to 3 is the vector space W. Then we had this linear transformation defined as T of P is equal to d squared P dx squared, the second derivative of P. And we found the null space of T consisted of all linear polynomials P belonging to F 4 x, such that P x is a naught plus a 1 x, a naught a 1 scalars. And the dimension of this space is 2, because the polynomial 1 and the polynomial x span the space and they are linearly independent, and so these two form a basis. So, dimension of n T we found as 2, and that is what the nullity is. We also had the range of T, because we differentiate twice we lose 2 degrees, and this led us to the fact that it is the space of all polynomials of degree less than or equal to 2, and therefore, the dimension of range of T, which is the rank, was equal to 3, because F2 the polynomials of degree less than or equal to 2, for this subspace we have the polynomial 1, the polynomial x and the polynomial x squared form a basis, and there are 3 of them, and therefore, the dimension is 3. Consequently, we get rho t, the rank of t, plus nu t, the nullity of t, is we have rho of t is 3, we had nullity of t is 2. So, 3 plus 2, which is 5, which is the dimension of F4, and which is what dimension of V is, because V in this case was F4. So, again we have rank plus nullity is equal to the dimension of V. This is a very important theorem which will be very useful in many of our proofs later. So, this rank plus, so we will conclude this again by restating just rank plus nullity equal to dimension of V, okay, the dimension of the domain space. For any linear transformation, rank plus nullity equal to dimension of V. We shall now use these facts and look at the linear transformation in various angles. So, let us look at now a vector space V and a vector space W. Let us deal with finite dimensional vector spaces for the time being over a field F. Let us say dimension of V is equal to n and the dimension of W equal to m. So, we have two vector spaces, both are finite dimensional, one of them has dimension n, the domain space, and the codomain space has dimension W n, and we have a linear transformation. So, we have the vector space V and the vector space W, and T is a linear transformation from V to W. What does T do? T takes a vector x and maps it to a vector T x here. So, we can think of T as a coding. It codes a V vector as a W vector. The vectors in V are all coded as vectors in W. So, T can be thought of as a coding of V vectors as W vectors, V vectors as W vectors. Now, is this a good coding? What do we mean by saying that is this a good coding? So, let us ask certain simple questions about this coding. Suppose I had a vector x which went to something here and a vector y which also went to the same thing, T y was also equal to T x. Then what we would have done is, we would have coded the vector also x as T x, we would have coded the vector y also as T y, and therefore, if at all at any time we have to decode, we will be in confusion whether to decode this point, as x or whether to decode this point as y. In order to avoid this confusion, we would like to have this linear transformation T to have the additional property that if an x goes and sits somewhere, no other fellow should go and sit there. In other words, if x goes to T x and y goes to T y, and if x and y are different, T x and T y should be different. Okay. So, therefore, the T x will be equal to T y only if y and x are the same. In case they are different, it must be different. So, in order that different vectors in V have different coded versions, we need T x, the code of x will be equal to the code of y only when x equal to 1. We would like to have T x equal to T y only when x equal to y. Now, not that all linear transformations are like this, there are bad codes and there are good codes. So, if you are looking at this from the point of view of coding, then we would like to have T to be a good code and hence this property. Any linear transformation which has this property is said to be 1-1 linear transformation. So, this leads to the following definition. So, definition, let V and W, in fact, this definition did not ever use that V and W are finite dimensional spaces. We will only specialize later to finite dimensional spaces. So, let V and W be vector spaces over F, T mapping V to W, a linear transformation, is said to be 1-1 if T x equal to T y implies x equal to 1. It is the same thing as saying different vectors in V will have different images in W. That is x not equal to y means T x not equal. This thing is the same as saying that x is not equal to y means T x is not equal to T y. So, this is same as saying asking x not equal to y implies T x not equal to T y. So, different fellows must have different images. Such a linear transformation is called 1-1 linear transformation. Let us look at a simple property of such a 1-1 linear transformation. Okay. Suppose T is 1-1. V is a vector space, W is a vector space, just like here V is a vector space, W is a vector space, T is a linear transformation, and suppose T is 1-1. What does that mean? This, let us now look at how the null space of T looks like. So, we have x belongs to null space of T implies T x equal to theta W, because something gets qualified to be in the null space of T only when it gets mapped to the 0 vector. On the other hand, T of theta V is theta W since T is linear, because a linear transformation we saw always takes the 0 vector to 0 vector. Comparing this T x equal to theta W with this theta V equal to theta W, we get therefore T x equal to T of theta V, because both are theta W. But T is 1-1, T is 1-1 means different fellows should have different images. So, here x and theta V have the same image and therefore, x must be equal to theta V, because if x were not theta V, then x will have a different image from theta V, but x and V have the same image and therefore, they must be same because T is 1-1, since T is 1-1. That says, the only vector which is in the null space of T is the 0 vector, because if x belongs to n t, it has to be the 0 vector. So, therefore, we get n t must consist of only the 0 vector, therefore, the dimension of n t must be 0 or the null space of T or the nullity of T must be 0. So, the nullity of T must be 0 if T is 1 1. So, hence we get T is 1 1 implies the nullity of T is 0, that is the null space of T consists of only the 0 vector. Now, if V is also finite dimensional vector space and T is 1 1 from V to W, we are not assuming W to be finite dimensional, we are assuming only V to be finite dimensional. So, let us assume both to be finite dimensional to be precise now. So, V and W are also finite dimensional vector spaces. So, V and W are finite dimensional vector spaces. By rank nullity theorem, we have rank T plus nullity T is equal to dimension of V, that is the rank nullity theorem. Now, if T is 1 1, we have seen that the nullity is 0. If T is 1 1, we had the nullity to be 0 and therefore, rank of T is equal to dimension of V if T is 1 1. So, therefore, the conclusion is T mapping V to W 1 1, V and W finite dimensional vector spaces, we will deal only with finite dimensional vector spaces now, implies many things, namely 1, the null space of T consists of only one vector, consequently the nullity of T is 0, consequently the range of T, the rank of T by the rank nullity theorem must be equal to dimension of V. Now, let us see the consequence of 3. We have V here, we have W here, T is 1 1 linear transformation, the range of T is a subspace of this, but this must have dimension V. If T has to be 1 1, the dimension of the range of T, which is the rank of T, must be equal to dimension of V, but we know that the rank of T must be smaller than or equal to dimension of W. We have dimension of range of T less than or equal to dimension of W, and therefore, rank of T must be less than or equal to dimension of W. But if T is 1 1, rank of T must be equal to dimension of V, and hence we must have dimension of V must be less than or equal to W. Okay. Hence, dimension of V must be less than or equal to W. Therefore, if for any reason dimension of V is greater than dimension of W, there is no chance of having a 1 1 linear transformation from V to W. Hence, we cannot have a 1 1 linear transformation from a vector space to a higher dimensional vector space, to a higher dimensional vector space. The dimension of W, I am sorry, to a lower dimensional vector space. to a lower dimensional W, because we wanted dimension of V to be smaller than the dimension of W. So, the dimension of W must be bigger than dimension of V. If for some reason W has dimension smaller than V, lower dimensional space, then there is no chance of having a 1-1 linear transformation from V to W. We will now look at an important property of 1-1 linear transformations. We will just mention it first, we will look at what that imports, a property of 1-1. So, we have a vector space V, dimension of V is n, and vector space W, dimension of W is m, T linear transformation which is 1-1. Since we have 1-1, it is a 1-1 transformation, a priori we must have that W must have bigger dimension than V. So, we are assuming that n is less than or equal to m. Now, suppose I look for a basis in V, how many vectors it should have? Since the dimension of V is n, it should have n vectors. So, let us say I have a basis. If I have a basis for this and then I look at T u1, then I look at T u2 and then look at T un. This will all be different vectors in W, because since T is 1-1, different vectors go to different images. So, if you look at T u1, T u2, T un, u1, u2, un are linearly independent in V, because they form a basis, they must be linearly independent. So, they are linearly independent here, and their image, will they be linearly independent? So, the general question is, if u1, u2, ur not necessarily a basis, look at linearly independent set in V, then can we conclude that T u1, T u2 etc., T u r is linearly independent in V, in W? And the answer is yes, and it is the 1-1ness that gets us to the result. Now, this would help us to connect again the rank and the dimension of V. Similar to the notion of 1-1 is the notion of onto linear transformations. Just as we saw, 1-1 means different things go to different images, and onto transformation means all the vectors in W will be used to coding, and therefore, every vector in W is the coded version of some vector in V. And what are the consequences of onto? We study, leave it here.